to introduce Dr. Leigh Orff, who's been to the Weather Summit before. He is a scientist at the University of Wisconsin, and he focuses on severe weather, including supercell thunderstorms and tornadoes. And I'm told you have some pretty cool visuals for us to look at today.
I think they're cool. I'll let you guys be the judge. Well, thanks so much for inviting me here. This is my second Weather Summit. I think I was here in 2019. It's a real privilege to be here and give a talk for all you folks. So yeah, I'm going to give a talk today about sort of a whirlwind tour through a bit of how I got into severe weather, but mostly it's going to be about the latest research I'm doing. I'm going to talk about some early life influences. Every meteorologist in this room can tell me how they got into meteorology, right? Well, I'm giving you my story. It's kind of interesting, I think. Briefly go through my academic background, talk about what I've been doing over the decades, not just me, but other people simulating supercell thunderstorms throughout the years. And then I get into sort of the part of the talk where I try to compare the model data that I'm creating with these models and look at reality, look at videography. And also I compare to radars and such like that. But videography is a tool that is still useful this day and age. And I'll show you some of that, and then I'll just look at the intricacies of tornado genesis via simulation. I've simulated a supercell at ridiculous resolution that produces a ridiculously strong tornado, and now I'm looking at how the tornado forms. I've been looking at other things. So one of my earliest memories, I'm not kidding you, I've got evidence of this, but anyway, when I was 4 years old, our house got hit by lightning. My sister and I was 4.5 years old, my sister was 3, we had just taken our baths, it's time to go to bed. We have a Cape Cod house, my mom is with my sister in my sister's room, watching the storm out the window. I'm with my dad in my room, watching the storm out the window across the house. Suddenly, I don't remember hearing a boom or anything, I just heard my mother give off this blood-curdling scream. I turn around and I see glowing wires, insulation, burning paneling, my sister's canopy's on fire, my mom can't hear because of the concussion. She was like deaf for a day. She was okay though after. So that was my wake-up call to severe thunderstorms. And only a few years later, also in western Massachusetts, our house was narrowly missed by an F4 tornado, one of the most expensive tornadoes to date in the United States because it destroyed an antique air museum in Bradley International Airport. So at this point in my life, I'm thinking, maybe I should study weather because it's trying to kill me. I should probably get ahead of it. So my education, Bachelor of Science and a PhD at the University of Wisconsin. Go Badgers. Assistant professor at UNC Asheville for 3 years. Professor and did most of my academic career to date at Central Michigan University. And I've been a research scientist at UW-Madison, or like a research professor type person from 2015 until now. Okay, so this is the Springfield Union from the day after our house got hit by lightning. And I've highlighted a couple of things. Numerous reports of lightning strikes hitting homes. No injuries were reported. Gusts ripped town apart. High winds, storm knockout power. There's lightning. 3 children nearly hit by lightning. 2 children actually hit by lightning and killed by lightning. This was a big deal to me. And I got to quote Mrs. LePage, 80 years old, who says, after talking about how her kids were almost killed, or grandkids, but they had rubber-soled shoes that saved them in their garage, you know they're going to be afraid of lightning now. Yes, they will. I'm 55 years old and I'm afraid of lightning. I don't like lightning. I stay away from it. Am I 55? I'm close to that. I don't remember how old. I don't know. I haven't had a lot of breakfast. Somewhere around there. Okay, so this is the tornado now, not the lightning event. This is in day after my 11th birthday, actually. So you can figure out how old I am from that. The tornado kills 1, injures 400. This is the Windsor Locks tornado. This was weird on several levels. A, it's October. B, it's New England. Yeah, that's where I go storm chasing, don't you? No, it was a really unusual case. Fascinating setup. Only one paper's been written about it. And sorry for the image quality here. Those are destroyed homes. This was weird because I just got back from school. The storm was coming. I ran into my house. My mom's like, close all the windows. Smart mom. The storm came, and I'll show you the actual path, and I'll get into the real stuff soon, but this is fun to talk about. So this is the newspaper. This was the day after, so not too accurate. Here's Hartford and Springfield. Born in Springfield, grew up in this western part of Mass. This didn't go that far up here, but I will show you the actual path. So Ted Fujita, and I'll zoom in on this in a minute, actually analyzed the tornado's path, and I discovered this image about a week before I defended my PhD thesis. And then I was like, wow, this is cool. This is a misspelling. It's Windsor Locks. but he follows a tornado, and as Ted Fujita, you all know who Ted Fujita is, right? I don't need to explain to you. We'll have to like remove your license if you don't. But anyway, so here we are, the Air Museum, direct hit. Barograph, 8 millibar pressure drop aside of the storm. So this is over here. This is the path of the tornado. This is the strong winds, the damage path. But even 8 millibar pressure drop, probably a few hundred meters or maybe a kilometer away, is a pretty significant thing. So the meso is, onward we go. Suddenly this thing starts dropping downbursts, downbursts. This is two tornado, downburst, downburst. Connecticut, into Massachusetts, welcome to Massachusetts. Downbursts, that's where I live. Somewhere in that black dot, I don't know exactly because this is a crappy map, but I remember this. My backyard, there was a tree that was standing like this before the storm, and it was standing like this after. It didn't get knocked down, it got sort of pushed over. So I got sandwiched between a F4 tornado and a downburst. What do I end up studying for life? Downburst and tornadoes. I don't know. Life is weird sometimes, but this happened. I was there. It was weird, but we survived. But the Air Museum got destroyed, and that was the end of that. Okay, I started graduate school in 1990. This came out shortly after I started graduate school, and I saw this, and I decided, I'll animate it in a second. This is Robert Wilhelmson, a very important thing that was made. It took a one-person year to make this video. It was nominated for a, what's an Emmy? Is that the TV? I always forget. Yeah, I was nominated for an Academy. No, it was an Academy Award. I didn't get it. It was nominated. This was really hard to do in 1990. Okay, but I was like, I can't do that. B, I want to do that. That's where I was at graduate school. So, I think this thing just went to sleep. Oh, here we go. So instead, my advisor, he built a supercomputer, out of actual parts. And it was really hard to use this computer because it was before the modern age of easy computing, I'd say. But the idea was to create a laboratory like we do today with supercomputer. Like federal supercomputers, you get on the machine, you do work, any kind of work. He produced his own because we didn't have that yet. So this is a 50-meter simulation. This was basically my PhD thesis, looking at how downbursts, downburst 1, downburst 2, one starts a little later than the other. One is 2 kilometers apart. I studied a bunch of different configurations, but it turned out that this configuration produced some pretty nasty winds in this region between and ahead of the storm. And this was because we were studying the Dallas-Fort Worth crash in 1985. I think it was. The whole plane came down, it encountered wind shear, and we think it may have flown between 2 downbursts. It didn't actually encounter a real downburst. But anyway, that was my PhD thesis. I started at CMU at this point. At this point, I'm running simulations, doing the best I can. I always want to run the highest resolution I can get away with, but there's no tools. The computers aren't very good, and the tools to visualize them aren't there yet, so I had to use a ray tracer. Back in the 90s, PoVRay, I don't even know if it's used anymore, but it was made to look at cool scenes of reflected globes and all this weird stuff. Well, I turned it into something where I could do isosurfaces. So here is, for instance, rain, hail, cloud. And I'm just trying to do kind of what Bob Wilhelmson did, that earlier thing. This is my sort of attempt at what he did. Looking at the cloud, the rain, the hail, the gust front, and I'm pretty pushing the computers to the limit, and I'm using software that wasn't meant to do this. I did some stuff with trajectories because I like those balls flying around. It's just cool things you could do with the Lagrangian approach. All these approaches that I did back in the early 2000s, I use these today, but I'm using more sophisticated tools, and a lot of the software was designed for science, not for making weird images like this. Anyway, fast forward quite a bit. This is from 2017. Now we're looking at a tool. The tool that actually visualized this is called Vapor. It's made at NCAR, National Center for Atmospheric Research. What I've done here is I've released parcels at different locations in the storm, and we're letting them go. I release them every 2 seconds, and this is the tornado, of course. Don't need to tell you guys that. This is a streamlined vorticity current, something that we discovered, and it's something that has been seen in nature. Like, there's been a couple papers that have already published about the SVC in nature. There's one field project called TORUS that's gone out, discovered SVCs. So this is a cool thing for me as a computational scientist to find something in the model that we haven't seen in nature yet, and then we find it in nature. Oftentimes it's the other way around, right? You see a tornado, but the computers aren't good enough, so then you have to write a model to try to simulate it. But this was pretty cool, and this is what I do. I just try to simulate with as much resolution as I can get away with. Now this is gonna go really fast, because this is old stuff, boring old stuff. I'm kidding. It's still pretty exciting. All right, that's tornado genesis. Rain over here, cloud. The surface is shaded by buoyancy. So it's cold, the colder the air, the darker the blue. So the cold pool of the thunderstorm, it turns out, comprises the air that makes up the tornado. I mean, you look at the core of a tornado, the air, look, see how it's always got that little cold thing around it? At least in my simulation, the tornado air, that actually ends up, it's in the cold pool, it's along the edge. This is just one environment I simulated. This is the 24 May 2011 El Reno, Oklahoma EF5 tornado simulation. I slow it down here just to show that cool anticyclonic vortex do a little trip around the main meso. You see stuff like that all the time. I mean, it turns out, and you'll see later in my talk, I think vortex mergers are super, super important. Now it's rain wrapped, right? That's bad. I think mergers of vortices are critical in tornado formation. They become less important as the tornado gets stronger, but I think they're key. At least, again, in my limited but very focused view. This rendering was done by David Bach at NCSA. He's wonderful software. He took my data and made it look beautiful. This gave me the impetus to do stuff like this. This is, I've been working with Hank Shima for a long time. You may know him as Pecos Hank on YouTube. He is a storm chaser. I would call him a professional storm chaser. He's not a university-funded researcher like I am, but I love collaborating with all sorts of folks passionate about the weather who are really good at doing stuff like this. So we did some comparisons, and I'm just like, wow, I guess we're on the right track here, because that's the model, that's reality, and on the next slide where they do Mattis clouds, you could be forgiven for not knowing which is which, right? Left is the model, right is reality. I may have shaded the clouds a little just to, no, actually that's not, I didn't, because it's David Bach. Here we have a tail cloud, something that is sort of roughly associated with the SVC, we think, and you can see little vortices that form along this. We see the same thing in reality. Here is one of my favorite sequences I've ever done, and I'll pause it right about there. So this is the forward flank of the thunderstorm. I guess we'd call this the left flank convergence boundary. I know supercells have so much lingo associated with them, it's very confusing. It's kind of like, just think of it as a boundary within the cold pool along the forward flank, or in the direction the storm is going. But this is pretty compelling. You have a horizontal vorticity, right, on its side. It's definitely streamlines, right, meaning it's going along the motion vector, and then it gets tilted up into the mesocyclone. And this wonderful sequence from Hank looks very similar. Again, Hank did this sequence to show the side-by-side stuff. I can't remember which tornado that was, but I mean, you got to admit, pretty good. We're on the right track here. And I'm very happy about that. You can see in this rendered image, you can see breaks. These are multiple vortices. You can kind of see through them sometimes. There's a crazy video online from this guy who got stuck on the side of I-90 during the Fairdale tornado that I used to show that shows how similar it is. Here, Hank is focusing on these little noodly vortices that are outside of the main tornado. You can see they're all over the place, right? There's all sorts of crap going on in supercells. It's amazing. Okay, so now we're going a few more years into the future, and I got to stop banging this wall. Now I'm trying to understand the fundamentals of what happens before the tornado forms, okay? So in this case, I don't want to look at all the trees in the forest. I want to look at the forest for the trees. So what I'm doing here is I'm temporally averaging data. Every single thing you see here has been averaged over 2 minutes in 1 second intervals. So I've got data saved every 1 second. I just do this moving average to sort of just see what stuff looks like over time if you just sort of smear it out. The only way I can get away with this is because the storm that I'm simulating, I follow the storm very accurately. So first of all, the pressure just drops like a banana. Isn't that a statement? Pressure drops like, no, I don't know. But this sort of weird shaped thing, notice how it's shaped, kind of curves off this way. This sort of end of this low pressure tube is associated with the streamlined vorticity current. Shortly after that gets set up, the tornado forms. This is the updraft. Pause it here. What you want, the stretching term in the vorticity equation, which I'm sure you all have tattooed on your left arm, is a function of the gradient of the vertical wind. So dWdz is large, which it is, 30 meters per second, 40 meters per second, 60 meters per second. dWdz big, yeah? Multiply that by the actual vertical vorticity, and that's the stretching term in the vorticity equation. So this tells us in a very back of the envelope sense that if you have the right setup, you can drop or grow vorticity exponentially, at least temporarily. So again, these are temporally averaged fields, so they look a little weird, but see there's like this little protrusion of pressure drop. That's the SVC. What I think is going on is that this pressure drop just increases the non-hydrostatic vertical pressure gradient force, or just say the vertical pressure gradient force. it really wants to force strong updrafts. That in turn increases the effectiveness of stretching to create more vorticity, and eventually it cascades into a tornado. Anyway, that's my theory of tornado genesis. It's a working theory of tornado genesis, or say a hypothesis. And we're in the process of a grad student working on this and other people working with me to sort of figure out the physics behind this. But this shows what's going on. Pressure, this is the pressure, it just goes crazy. Updraft gets really strong near the ground, streamlines vorticity. It tells a pretty compelling story. The thing in science, though, is we have to establish causality, not just correlation, right? And we use the word associated a lot in our field. You know, the SVC is associated with. That doesn't mean it's causing. We'd like to know the causality. That's always what we're looking for in meteorology, so that if we see something on radar, we know it means something. We can use that information to make a better forecast. That's really where all this work that I'm doing ultimately, hopefully, results in better short-term tornado forecasting, right? If we can get this stuff done better. So understanding the storm is a good thing before you try to forecast it. Okay, this next segment, I get contacted from folks a lot who want to share with me their own data, say professional and amateur storm chasers and people I just don't know. They're just very passionate. I don't know too much about Brian and Brandon, but I'm very grateful for their footage. They shared with me they flew a UAV or something, a drone, the entire length of the Mayfield, called the Mayfield tornado path. Now, when I got this, it wrecked my day because I just spent the whole day going, dude. So I'm gonna slap my own stuff up here. So we're moving with the storm, and I'm trying to just show an example of what might be going on, okay? Because obviously it's a different storm. But you'll start to see little scalloped regions, little scouring regions, hard to see. You'll see them soon, believe me. There's a little bit of evidence of damage there, a little bit, then there's a little one here. You see some branches down, and there's our first tree down, right there. So this is the beginning of the Mayfield, we call it the Mayfield tornado. It's a genesis. We're somewhere out, and I'm not in Kentucky yet. Now, what's really interesting with this footage, through that tree, is how the tornado scouring paths change when it encounters boundaries. Like now it's a multiple vortex. See that? It's already doing the multiple vortex cycloidal thing that you'll see my stuff doing in a second. The tornado undergoes different morphologies pretty quickly. And so here's another case where it goes from, I don't know what's going on, and suddenly you see multiple vortices. Now, there could be some difference in land use that would make the scouring more visible. I'm not an expert on that. But you have to admit, things seem to happen at boundaries, which is the same in models. Wow. Here's the best cycloidal image I've got, right? So now you've got and you look at what my stuff is doing, similar. Again, I love this because you can kind of picture what's going on and what went on by using the model as a guide, shall we say. Flipping it, sort of. Again, here's these paths. They hit some trees, then change. I know I'm jumping around. The tornado gets really narrow, probably single-celled again, encounters some trees, destroys some trees. Suddenly the path is a little wider, knocks down some more trees. So it's really interesting. And I gotta say, the modeling world fails miserably at handling the surface of the Earth correctly, myself included. All of us do this. The problem is we don't have the computing power yet to properly handle the surface. But actually we do. It's just that we haven't learned how to use it yet. Now we get into Mayfield, and this is where it's horrible, but this is where, the engineers, I work with wind engineers, and they're very interested in how the tornado affects buildings on a very short time scale. And so when you get to this sort of grisly part, there's still science in some of this. And this next sequence, I'm sure you've all seen, from Reed Timmer, put it on YouTube. I am fascinated by this. Now, nobody was hurt in this, but the way tornadoes destroy houses, they take the roof off. the updrafts are insanely strong. You can see it. The updrafts near the ground are like 50 or 60 meters per second. Our models aren't showing that because we don't have the resolution yet to do that. And then there's some beautiful, weird things going on here. I've seen this sometimes you see vortices, so this is like vortex breakdown or something. You see the very low pressure in this and it condenses, and this is a different view of the same thing, and I'm really amazed by how different tornadoes can look based upon what direction you're looking at. So Timmer had 2 drones at this point, and I think I've got them synced up pretty well. You might not believe me, but this is the same time almost, and they look very different. But it's interesting, the tornado sort of hangs out in one spot for a few minutes, seems to sort of get stuck in the trees and destroys the houses, then jumps over. It's crazy. But there's a lot, I will say, before I get into my stuff again, there's a lot to be learned from that little bit of footage there. I have to believe we can use that if we wanted to, if we had the resources to do the same thing they do in Florida and to put clips on roofing and to add a few dollars, I don't know how much it would cost, but that would probably save you from moderately weak tornadoes. If it doesn't lift the roof off, you might be able to salvage your home. I don't know, but there's very good stuff to be seen in that, and I'm thankful that nobody was hurt. This is a rendering of my own stuff shortly after the simulation was done. This is the "it's coming right for us" view, and so you can think of perhaps the view of a UAV following the tornado. And we can do that now. So it looks pretty good. I'm looking at the cloud field, and on the surface it's the pressure field, and I'm just basically leaving a trace of the lowest pressure so you can see the vortices doing their thing. This is pretty much state of the art, although I did this like 4 years ago, and I'm on a new supercomputer, and I just asked for a ton of time to do this more because I want to go beyond 10 meters. I want to go beyond what we've already done. So this was done on the Blue Waters machine at the NCSA in Illinois. This is a different view. I've kind of clipped through the cloud a little bit, but one thing I like about this view is when I was doing this, there's an image I'd seen online that I knew looked pretty close to what I had done to this, and it was the Mayfield tornado. And I'm like, you know what? That's pretty good. That's pretty good. And this isn't the Mayfield tornado, but you know, it's an EF5. Mayfield was an EF4. But again, I do this because that means the model is probably doing a good job. And you may say, well, it's obvious the model. No, it's not. Scientists are skeptical people, and you know, you'll get raked over the coals if you haven't done your due diligence. So it's important to me, extremely important to me, to not get lost in model land. Model la-la land, shall we call it. It's good to keep your eye on the physics of what's going on in the atmosphere, and that's why I collaborate with observational meteorologists, field meteorologists, both professional and lay, etc. I don't care. It's all fun for me. Different simulation, but I think a very important simulation. This is work done with Dr. Morgan O'Neill at Stanford University. We decided to see if we could create above anvil cirrus plumes, which are features that were discovered a few years ago on satellite that are linked to strong thunderstorms. While this image does not have an actual AACP, they look kind of like that. And yeah, this got us in science, which was pretty cool. So this work, if I can advance, we're looking at the top of the cloud now. And I gotta say, modelers in meteorology neglect the top of the cloud. We always put all our resolution near the ground because that's where people live, and that's where we want to make sure we get the physics right. But we don't have enough vertical levels, so we have really, really coarse resolution at the top of the domain. I'm like, no, we're gonna run the whole domain at 50 meters, no stretching whatsoever. Let's just fire it up, make the atmosphere up, go into the stratosphere, go up to 30 kilometers, and just let it go. And it created this. So this is the cloud field, cloud ice field. And I'm looking, this isn't exactly what you'd see from a plane because I'm looking at a higher version. But I wanted to show you higher value. It's a classic breaking wave. You're seeing the onset of a hydraulic jump. If you've seen water flow through a channel down a mountain or something for a reservoir, you ever notice how it sometimes goes from really smooth to suddenly really, really turbulent? That's the moment the hydraulic jump kicks in. When a hydraulic jump kicks in, the flow changes quite dramatically from smooth and shallow to turbulent and deeper. So a deeper but more turbulent flow. But what it does in the cloud here is it kicks a whole bunch of ice into the stratosphere. The stratosphere, as you know, is a very stable layer of the atmosphere. It's typically very dry. And this is a mechanism that gets water into the stratosphere, which is interesting to climatologists for reasons I'll explain in a minute. But and this is a higher resolution simulation I just did recently on the Frontera Supercomputer using a more realistic sounding. But the reason why we're interested in AACPs is they're a good nowcasting tool for severe thunderstorms. There's a paper that says, and there's a paper published that shows that in 75% of the cases where an AACP is seen on satellite, the storm is severe, meaning it produces large hail or strong winds, damaging winds. Not necessarily tornadoes, but something. So when you see an AACP as a forecaster, that can help you. Maybe, but we don't understand why they're associated with these. It probably has to do with the updraft and wind shear and things like that, and we're trying to figure that out. Our paper just sort of, the science paper just sort of scraped the surface of what's going on. We just basically described it, and we did some calculations of how much moisture gets in the stratosphere. But it's like there's a gravity wave breaking going on, and that sets up this environment that allows a thin jet to form, and then boom, the hydraulic jump. So as you see in this layer cake, and this is only one tiny piece, I'll pause it here, one tiny piece of the simulation, just focusing on the top of the cloud. Overshooting cloud top, This is very interesting to me. Notice how it's flat here? I didn't realize I need to save data above 21 kilometers, and there's actual cloud material 21.5 kilometers above the ground. You don't see that too often. That's interesting. Okay, that's interesting because we're in the stratosphere now. You don't have too many clouds in the stratosphere. But anyway, so this is early on. This is in seconds. This storm is only like a half hour old, and there is the onset of the real above anvil cirrus plume. The stuff you saw before that was sort of the precursor to just getting things set up so that happens. Again, this is still early days, and this simulation has yet to be formally analyzed. I've just visualized it. So now the same simulation, overshooting cloud top. I'm just looking at stuff above 15 kilometers. When you notice this region here where it gets really dark, there's a very sharp gradient between the moisture value and then dry air above it. When the AACP kicks in, you'll start to see cooler colors. Now you're up in regions where the cloud is there's less cloud, okay, but it's there. And I'm trying to show both very large values and small values in the same movie, and I use tricks to do that. But this region here, this is the above anvil cirrus plume, and it's doing weird things. And I only run the simulation out to like 45 minutes, I think, but I want to simulate these out to a couple hours. I want to see how the water gets into the history of the water, all this stuff, and of course, look at the link between the AACP and severe weather in the storm. So this is like the beginning of future work. And this is really cool. This is vorticity, and I'll show this twice just because it's cool. So I'm just rendering vorticity. Here's the overshooting cloud top. This is only 15 minutes into the simulation, so it's just the first big updraft. This is when you start seeing the cumulus congestus goes into a big supercell. It's turbulence. We're resolving turbulence, essentially. I mean, you see all this noodly spaghetti stuff. Those are just vortices, just spinning and twisting around. Here you have that wave breaking causing this cascade of this portion between the AACP and after the wave breaking is still, I have to work that out. But clearly there's things that go on that sort of get the environment in a state where this hydraulic jet kicks in and boom, you get this big AACP. So this is work that I think is one avenue I'm working on along with just tornadoes. So I zoomed in here just because for the folks in the back of the room, you can see this weirdness.
That looks like Reynolds' brain last night at the bar.
Thanks, Rob.
There you go, man. There you have it. But it's neat. And the reason I'm able to, I've developed techniques. This data is sitting on a hard drive on a supercomputer. I've actually got it backed up. It's only a couple hundred terabytes. Yeah, really. Pause for laughter, yeah. No, it's a lot of data, which makes it a real issue. But I've done all sorts of things to compress the data, and I do all sorts of ways to make the data smaller. But it allows me to do, I could render this again. I could give you another movie and make it purple if you want. I mean, in other words, I can go back to the data and I can bring it back to life. So there's a ton of data to be studied in this simulation. It's not like the simulation's done. In the old days, people would do simulations that were like, they call them hero simulations. They'd make a movie and the data would just get thrown out because they don't do with it, okay? In this case, I can save the data, I can share the data. Obviously, it's many years into the future now from that, and we have the more computers. But this kind of stuff with this kind of fidelity is kind of new, and I want to study the tops of supercells as well as the bottoms, and even the middle maybe. But the top is definitely the place that gets ignored the most by modelers because we figure what happens after it hits the anvil, who cares? It doesn't matter. We have to focus our resolution near the ground. This is the 10-meter simulation. This is the cloud field. I've done things with volume rendering so you can sort of see both small values and large values. So we're under the storm, basically under the ground, looking up, and you go, where is the tornado? Let's see. Where is it? Has it started yet? Look for something kind of like a tornado. Let's see. Isn't it cool, though, how it really looks like a storm with the updraft, just the cloud just forming out of nothing, just like with real storms? There it is. So there you start to see, this is in the cloud field. So again, there's better ways to render tornadoes, but let's render the cloud field. The center of a tornado has the highest amount of cloud water, so you see this like dark thing. I did that on purpose because as this tornado becomes a multiple vortex tornado, you'll see it does some really interesting things. At this point, I'm just saturating the color map, but you'll start to see that core start to wobble. Starts to wobble a little bit. I know from footage of tornadoes that not all tornadoes take a while to become multiple vortex. It seems like some almost fall out of the sky that way. This tornado starts out as a single-cell tornado. It sort of gets bigger over time and becomes a two-cell tornado, then a multiple vortex tornado. I think this is just one example of what happens. I'm no way, shape, or form am I trying to imply that, this is how all tornadoes form. No way. First of all, not all tornadoes are high EF5s, right? But I want to focus on these, and I think there's a good argument to be made to focus on the high-end ones first because they disproportionately cause the most damage and death. You can have 100 EF0 tornadoes, but one EF5 in the wrong place, that's bad. But now you can really see the multiple vortices in the cloud field. I really like this part of it because you can really see them come and go. And it's kind of designed so you can see through it. Again, I'm trying to render both small and large values, which is challenging. But this is simulations on disk. I've only basically begun to scrape the surface. All sorts of plans. I'll show you as I get towards the end of the talk, which we're getting there, where I'm trying to follow individual vortices. And my future plans are I want to be able to actually treat vortices as objects. Find the vortex core locations, create a data object. If it's a merging event, try to actually treat them as things, and then we can start to do some interesting statistics and other physics. So yeah, I'm showing you this whole sequence because as you see, and this, of course, the whole thing is moving, but it changes its morphology quite a bit over time. Now I'm really trying to focus on what causes the tornado in the first place. What is going on during tornadogenesis? This is the last segment of the talk. What's going on? So right now I'm looking at pressure perturbation fields. So I'm using 3 different isosurfaces effectively here. So it's the same scene, just looked at 3 different ways. The little green nubbies, those are drops in pressure, but I'm shading them by vorticity magnitude, which may seem weird, but I don't know, it seemed like a good idea at the time. Where you have low pressure from a whirling vortex, you'll also have large vorticity, but this just kind of shows it in what I consider an interesting way. So what happens? Let's watch it, because really the only way I can describe what happens is to show you. It's kind of silly just to talk. So you see some vorticity on the ground first. At this point, this is where I consider the genesis of the vortex that leads to the tornado. I don't call this tornado genesis because we don't have a tornado yet. The winds on the ground aren't strong enough. So it starts out, you can see the path of the vortex on the ground. You're starting to see it in the pressure field. But what's the most important thing to me is you're seeing something 2 kilometers above the ground and on the ground. A lot of tornadoes that don't grow, I think, never get a connection to the heart of the meso. And in this particular case, a couple of interesting things occur. So this is what I consider the beginning of the event. Let's see if we can get it to advance. But no, one vortex merger. That just happened. You'll see it closer again. Now we have a tornado. So you'll see a red T pop up when the winds reach tornado strength. Second vortex merger. And the third vortex merger is coming up right there, and I'll focus on that because it's the most important one in my opinion. It actually takes this young tornado and sort of brings it into the fold of the mesocyclone, and you'll see what I mean in a second. Now I'm looking at storm relative horizontal wind, the volume rendering, and painting it on the ground as well. What would radar see if it was looking at this? Basically the tornado threshold winds. So a lot of meteorologists are interested in how, I think it's a false dichotomy, but they say, do tornadoes form from the ground up or from the top down? And I'm here to say, yes, they do. And that's kind of the issue. So you see a lot of stuff going on near the ground. This is wind speed now. So pretty much now, at this point in this tornado's life, it's actually not a tornado yet, or yeah, it is. If you were to scan this with a radar, it looks like the velocity is about the same all the way up to the top. Okay, pretty uniform velocity. But no, it's really not a strong tornado. Then you see this huge pulse of EF5 winds kind of go from the bottom up. So that is of interest to some people. I think it's more complicated than top down, bottom up. That's why I want to.
How high up are you saying those winds are going? Like if you get that F5, how high up are those winds F5 going?
I'm looking. So this is in kilometers. So let's see.
Oh, okay.
That's 2.3 kilometers at this point. So we're at least up. We've got EF5 winds at least 2.5 kilometers above the ground. Yeah, don't fly through that. So here is the same scene showing these 2 things together. The vorticity / pressure drops, and then what the radar would see. So you see it in the vorticity before you'd see it on the radar. That's kind of my point here. What I mean by that is there's some subtle signals in the wind field that probably wouldn't be detectable with radars, but we see them in the model, meaning they're detectable. We just have to figure out how to detect them. And let's see, what's next here? Here's where again, another way to show this, I'm looking at tornadogenesis. This is the vortex that becomes a tornado. We have one merger right there, and they're important. I'll show you in a second later. Second merger from this vortex that's kind of just hanging out, just kind of gets assimilated into the developing tornado. And then here's vortex merger 3, the most important one. Now watch what happens here. It's like it zips up. It like forms a tornado from 2 vortices and brings them together, coil together. That is cool. I mean, I've never seen anything like that before. For the remainder of the talk, I'm going to show you my latest approach of trying to follow what's going on along the vortex as it happens. So I wrote some simple Python code that just, you give it a vortex seed location, and you find a little patch of space, and you go up, you find the lowest pressure. Like you start it with a low pressure, and then it follows that little low pressure bump, and you go as high as you can, and you hope for the best. And it works pretty well, although it's a pretty dumb algorithm. But I want to show you at least what this is about before I start animating it. So this first set, I haven't actually, this is before the algorithms really worked very well, but I wanted to show you what's going to start. Now watch what happens. Okay, we've locked onto this vortex. Now remember, I'll pause it. We know this isn't a tornado yet. We've just shown you that the winds are too weak for it to be a tornado, but there's a vortex, and I can track it, and I can see what's going on during tornado genesis. That's why I'm doing this. And there's the mergers, you'll see them, I'll focus on them. This box that keeps on wobbling around shows you the extent of this vortex, and you'll notice it's highly tilted at the beginning. Notice how big that box is, because look at up on top, it's way tilted. But then as it gets super strong, it all gets very vertically erect, and it becomes more of a monster. My algorithm starts to fall apart when the multiple vortices kick in because there's different low pressure centers, but it works pretty well. Now, this is what I presented some of this at Severe Local Storms Conference. Now that I've got the location of, I gotta pause that, it's just too cool. Now that I've got the location of the center of the vortex, I can do calculations there. One of the first things that jumped out at me is, it looks like a super adiabatic layer on a SKUT, doesn't it?
Yeah.
I call it a vorticity lapse rate for lack of a better term, but isn't it weird, and it almost makes you think it's like an artifact of the boundary, the surface boundary, but I don't think it is, how you get this local region of the strongest vorticity in the entire vortex is right at the surface. That's important, okay? It doesn't always look that way, but I know it's important. We've got a merger, see that little, you'll see, I'll focus on this a little more, but the pressure's on the right. Watch the pressure just sort of lazily go to the left. There's a point at which when the pressure at the surface is the lowest, it doesn't go so lazily anymore, it just kind of hauls ass. So the pressure drops quite quickly in the tornado once it really starts to spin up. But to my knowledge, no one's ever done anything like this, where you actually do a vortex relative analysis, a very simple analysis, of a tornado. So yeah, what is up with these? I don't know yet. I see this, they seem to be sort of associated with these mergers maybe, but they kind of go back and forth, and sometimes you get these waves, and you see them both in the pressure field. So there's definitely some interesting things to dig out of this data. I'm just looking at the bottom 200 meters now, okay? Focusing on the same regions, looking at those vorticity lapse rates, right? I still don't know what to call them. And again, focusing just on the bottom now, same animation. So there's, that little, could you catch that? I'm gonna show that again in case you missed it, because I wanna show you something really interesting. Right there. So my algorithm jumped onto that seed because that was the lowest pressure, jumped from that one to that one and went up, and then it jumped back to that one. So a vortex merger event happened, and my algorithm shows it pretty well because it's like, oh, you're stronger than you. You know, it's a dumb algorithm, but it works pretty well to capture that. In the future, I would like to be able to capture more vortices and then, like I said, turn them into objects and do things. I don't know what things I'm going to do yet, but I got to do something. But yeah.
Do you see this with like non-tornado producing supercells too? Or?
This yeah. In fact, you do see the small vortices swarming around. Absolutely. I haven't simulated a lot of those or focused on them because I'm focusing on the EF5s, but all that stuff. But no, the truth is there's swarming vorticity in supercells, but there's not always tornadoes. I think that's where things like the SVC come into play. There's coherent features in the supercell's cold pool that are being slurped into the updraft, for lack of a better term, and these boundaries actually dynamically can actually affect how things go. This is the cutting edge now. We have people out in the field looking for SVCs and trying to link them to tornadoes, but we're trying to answer questions like what you're implying is, hey, if storms that don't produce tornadoes don't show this, maybe we can use that. But no, you got tons of vorticity in non-tornadic supercells. You just don't have tornadoes. Here I'll pause it really quickly. I know I'm blowing through a lot of stuff. I felt like I guess I don't have to talk so fast, but I just do. I just can't help it. What I'm doing here now, so we're looking at just another way of looking at the same simulation. I'm using volume rendering. So I try to show really low pressure, less low pressure, and then just ambient pressure. I'm showing you a very transparent my algorithm just to show you where the tornado is before there's a tornado. Again, just to try to look for things that might be interesting. You'll see some of these multiple vortex or these mergers going on in the pressure field. One of them, the third one, this is vortex merger 3, where you see this tornado is very strong aloft, and then it just kind of zips it up, and you've just made a tornado, a big old EF5. Fast, and there's another vorticity lapse rate. So looking at it from the top down, this shows how the initial vortex that arguably is not the tornado but you'll see what I mean. At the top, at first it's right in the center of the meso. It sweeps way the heck out to the periphery of the meso. But what happens then is there's vortex merger 3. You see this drop in pressure that's near the ground. That then just, watch, it snaps. The algorithm snaps into that, and now it's a big old monster EF5. But what just happened there is fascinating to me. You had one vortex that had a couple of mergers near the ground, and then there's one merger that happens aloft that had that merger not happened, I think this tornado wouldn't have just fizzled out because it wasn't connected to the center of the mesocyclone where all the energy, the kinetic energy of the storm is. So yeah, this is cool. I mean, there's just so much to unpack with all this data, and that's what makes it fun because I've got lots of data to play with. I'll show that one more time. I went too fast. The vortex merger, I guess I didn't. I went the wrong direction, sorry. I wanted to show you that vortex merger. It's just so cool. Boop. I don't know. It doesn't go boop, but it might in my code. I might have to do that. So yeah, looking at the ground up now, there is a top kind of getting off, and then it kind of gets pulled back into the center of the strongest vertical winds. So here's the updraft in the cold pool, along with the tornado or the tornado vortex. So you can see where it lives. The tornado lives in the cold pool along the edge, basically along the inflection point between the rear and forward flank. It sort of starts out behind that in this simulation along the left flank convergence boundary. No, basically, it's right here. Here's the cold pool. One of the interesting things about this simulation, in my opinion, is that the cold pool looks like it's got air masses, right? You've got the ambient, you've got the diffuse out here in the forward flank, you've got the really cold air in the center here with the left flank of the storm. The rear flank is actually kind of warm. Many of the downdrafts in the rear flank, which doesn't appear incredibly important in the simulation, they tend to be positively buoyant, I think, because of subsidence. You've got dry air that's being pushed downward. In my last sequence here, looks like fire in a fireplace, but it's showing the cold pool and showing again the relationship between the tornado vortex, or the vortex that becomes a tornado, and the cold air in the cold pool. It used to be thought that tornadoes couldn't form in the cold pool, maybe because the cold air is too cold, but it's basically a Goldilocks thing going on, where, yeah, it needs to be cool, but not too cold. We're still trying to work all that stuff out. And finally, this is the last sequence. Now we have I'll pause it here. We have the vorticity field and the location of my vortex. So you better bet there's a little thing around that thing. There better be, or my algorithm was wrong, but it's not. You can see. Again, I'm tracing the vorticity along the tornado and the pressure perturbation along the tornado. And this sort of mess here is the streamwise vorticity current. And it looks more turbulent in a 10-meter simulation than in a 30-meter simulation, which is what you'd expect. So, man, I talk fast. I apologize for that. Closing thoughts. Little time for questions. So we've come a long way since the early days of supercell modeling. Hopefully I've shown you that. I have to really think back to Bob Wilhelmson's work with his model and my advisor, and they're creating models on supercomputers they built. You know, these folks did the hard pioneering work as far as I'm concerned. I jumped on and I grabbed on and I, for dear life, and managed through nothing but stubbornness to create a software environment that could handle this type of simulation. That's the best way I can describe it. I got a handle on I/O if you really wanted it. I/O will kill you. But anyway, that's always been the case. We've come a long way. At this day and age, in 2023, we now have supercomputers that can do what you just see with relative ease. It's still a pain, but it can be done. You have really new and exciting observational techniques now. We're flying UAVs in supercells, man. We're sending drones, we're selling copters, everything we can throw at it. We need in situ data. Radars don't tell you what the potential temperature is. You got to get in there with in situ data. So we've got all sorts of stuff going on. There's a convergence of technologies that makes me very optimistic that we are going to get a handle on tornado genesis within the next 10 years, or at least handle the surface right, and then so our tornadoes are as physical as we can do. When I say UAVs and GPUs are the future, I'm being a little silly, but it's actually the present. But what I mean by that is we've just started to in the last say 10 years or so, really focus on flying things into supercells, not just bringing radars to near them. GPUs are graphical processor units. We now can run models on GPUs. So the graphics card in a PC has a GPU on it. These have been weaponized by NVIDIA, for instance. They build computers out of them. You could write code for GPUs. There's a model called Fast Eddy that NCAR created, and they just open sourced it. They announced it at AMS. I was so happy because this model is native to a GPU. When I say we're going to be able to do tornadoes right in the next 10 years, I think, it's because we'll have models like Fast Eddy running on GPUs linked to models like CM1 on a supercomputer. It's going to be crazy. I have no idea how the hell I'm going to do it, but I'm going to try. So, in short, why do we do this? Why in the world is this just to so I can have fun? No, of course not. We're trying to predict tornadoes better. You guys more know than anyone else how sickening it is to have to stand in front of the camera and announce to people how all this bad stuff is happening. But if we could predict it better, you could talk specifically to that one neighborhood and say, whatever, go to your safe space, whatever. But you wouldn't have to worry about evacuating the entire city because we've gotten better at this. That's where we're going, slowly but surely. We will get better at this. The false alarm rate will go down. It's going to take a lot of time, though, because there's not like governmental politics, but there's scientists understand the false alarm rate problem very well. They know you can easily make it go down by just missing more tornadoes. We don't want that either. A false alarm is better than no alarm when there is a tornado. Ask Plainfield, all right? Ask Windsor locks. They issued a severe thunderstorm warning an hour or 15 minutes after Windsor locks. In Plainfield, I think it was the same. Now, I can't get too hard on people from that time because the technology wasn't there, but we really need to do that better. And I'm hoping that eventually the work that I do, playing on computers and making these crazy movies and doing this analysis, eventually that research should filter research to operations, right? R2O. I'm hoping, that's a NOAA term, but I'm hoping that that's where this work will eventually end up, hopefully, making better forecasts. And that's where I'll stop and say, hey, thanks for listening, and I'll take any questions.
Have you ever tried to do the pressure field modeling with merging supercells before?
I have not yet. No, I haven't done that yet. I'm thinking of, I know what you're thinking about, I'll bet. What's the big 2EF4s? I'm just drawing a blank. The one that was in Nebraska? Pilger, Nebraska. You remember that storm? That was one supercell, not producing two cyclonic tornadoes, but yeah, mergers are interesting. I don't think, I'm not as interested in mergers yet because sometimes they're constructive, sometimes they're destructive. A lot of times there's this idea that, storm mergers are going to, things explode. Occasionally that happens. Mergers can result in storm dying too because you've got updraft, rear flank, downdraft. How do you get those to come together, right? The updraft of this storm and the updraft of that storm have to go through a lot of mess before they merge. I have not done those. Those types of simulations will arise when I have figured out more of the simpler stuff. I guess that's how I'd say that. Another question? Back of the room.
Just comments.
Sure.
You're fascinating.
Well, thanks.
You're amazing. Your work is incredible. That was a great presentation. You're going to save a lot of lives.
Well, I hope so. I mean, I don't think of it that way. I'm interested, as a scientist, it's just fun. I'm a kid playing in the pool, right? But I've somehow found this little niche where I'm good at it, and people think it's important. I guess it's important. I think it's important. And I'm funded. Yay! That's the hardest part, to be quite honest. Getting funding is the hardest part and the most part that gives you heartburn. But so far, so good. And thank you for your time. I really appreciate it. I also appreciate just having the opportunity to talk to you guys, because you guys can help save lives too. I mean, I don't get, you guys get a ton of credit for that, for bringing these things to the public. back there. Yes.
How quickly are you modeling a tornado environment after a storm? Like you did Mayfield, obviously.
Yep. No, I didn't. But I did. Here's what I tried. I have a graduate student. So I want to be clear. I didn't actually. The storm that I simulated was El Reno, but I showed Mayfield because those dudes sent me that wonderful drone footage. So okay, go ahead. Finish your question.
No, that was it.
Oh, okay. Okay, Derek. So I didn't answer. What was your question? Please.
How quickly?
How quickly? Oh yeah. Okay. So the reason. Sorry, I get fuddled. Yes, we can go a day after a storm. I can go to like the RAP model, get a sounding, throw it in the model. My grad student Kelton Halbert did that with the Nashville tornado, and he actually got a friggin' tornado. I don't think he's going to publish it though, because anyway. But we did that a week after the storm, maybe. So we actually can do this now. If we can get the data to initialize the model right, I can create these highly idealized, horizontally homogeneous base state simulations and sort of try to recreate storms. I do want to try to bring storms back to life to the point where it actually isn't just a supercell, but it's like, yeah, that supercell looks a lot like El Reno. I mean, the El Reno does look a lot like El Reno, but a lot of EF5s look about the same, big-ass wedges with multiple vortices destroying things. But yes, we can do that now. I tried to do Pilger, produced a beautiful thunderstorm, and it went dissipated. I'm like, I'll try that one again some other time. So we've tried different environments. Most don't work. The thing that made this work significant in the first place was the fact that I got the damn tornado in the first place, because it was hard to get the tornado. We were running out of computer time. The model was doing weird things. My model had bugs in it up the wazoo. I should write a book. I don't know. But it was interesting. But we got it. And now that you know that you can do this and you know that we can get realistic looking tornadoes with models, that was a really important thing. And now we could just start from that point and do better and better and better. So, Derek.
Yeah, long time listener for
Yeah.
calls. Is streamlined vorticity current, is that your own term? Is that something that
Yeah,
you're focusing a lot of your research on this?
yes. So the SVC is a term that we came up with in our BAMS paper. I remember this very clearly. I was talking with Bruce Leigh and Kathy Finley. They're my collaborators along with Adam Houston on that paper. And I've been looking at this beautiful, I'm looking at my own renderings and they see this like glob that goes up and around. I'm like, that's a thing, we gotta call it something. I kept on calling it this horizontally, this string of words, but we had to call it something. So I'm like, it's a streamlined vorticity stream, but we can't call it that. And then Bruce said, how about a current? I'm like, perfect. So it's nice when you have an acronym, but there's too many damn acronyms in mesoscale meteorology already. And I didn't really want to add another one, honestly, but we did, and it is important. It turns out that they exist. So that's where I started feeling better about SVCs until worked at Texas Tech. I'm thinking of, again, I forget names bad enough when I'm not in front of people. Alex Sheath at Texas Tech with Chris Weiss, his advisor. They've gone out with radars, done RHI scans and PPI scans. They've done modeling and they've found SVCs so they exist. That's good. In other words, this isn't model la la land. This is probably pretty good. So yeah, we discovered it in the model, and then it was discovered really in nature.
Well, this is why it's fascinating to me, because I feel like you're having ground truth from storm chasers, observing certain things, your data, the theories,
I'm trying to bring it all together, man.
So now that you're getting these confirmations on the ground and also with your work, are we like starting to understand those perfect environmental conditions before EF5?
Here's the
early lead time.
Yeah, right.
And on that stuff now? Or?
The problem is, you said environmental conditions before. We've tried for years, we talk about SRH, CAPE, and all that stuff. Those are like horizontally homogeneous terms before the storm forms. We've tried to estimate tornadoes from environmental parameters for years, and it doesn't work very well. So what we're looking for more realistically is, okay, what does an SVC look like on radar? Now that we know they're important, let's see if we can detect them. Okay, we've detected them. Now, and this is the work that really is important, why are SVCs important in the first place? We've provided an argument that they're important for a certain reason, but we still haven't gone through the real rigorous, we haven't done the really quantitative analysis that needs to be done. This is work in progress. But yeah, I'm very conscious of the fact that we discovered this, and I'm hoping that it was, by giving it a name and everything, it's really important. Because as a scientist, I'd hate to find something and say, "Yay, look at this," and then it's not important. And that happens in science all the time. Theories are destroyed. Some people don't like my work. because it destroys their theories. I'm sorry, man. Theories are meant to be destroyed. This is science. I want my theory to be destroyed. I relish that. That means we learn something and we push the science forward. So, yeah, I don't know if I answered your question, but yeah. Yes, sir.
He was way before me.
Okay, Matt, go ahead.
I was wondering how you define when you put the T there, tornadoes formed, what your criteria is.
I looked at the EF0 threshold for ground relative winds. Really boring. So the first time we reached that threshold, I just say it. And then it does get stronger from that point. So I would painstakingly went through each frame because I wanted to, it looks like there's a tornado, but there's not. I wanted to show you that technically it's not a tornado yet. Now it is, but see what happened before that tornado. Knocked over the podium. What happens before that tornado is super important, and that's the point I want to really focus on.
Because you said a couple times, we don't have the wind strong enough, but you're showing this coherent.
It's not a tornado yet. It's not a tornado yet. Technically, that's important. I
If
think.
we had like super fine dust
Yes.
in the atmosphere,
Yes.
would we see this
Yes.
non-damaging, very weak
Probably.
tornado
Yes.
before we actually have a tornado?
Yes, I think you would. You see those already. And this is where, again, I love working with Hank Shima, and other storm chasers who actually are crazy and go out there and get too close to the storm. They're going to do it anyway. I just say, be careful, guys. You see those little cloud tags in the forward flank, like little tiny little dust whirls? They're out there, man. The world is swarming with vorticity. I mean, that's a silly thing to say, but move your arms around and you make some vorticity that's stronger than we have in a tornado. It's just over a tiny little region, right? Circulation's another story.
So do you think a lead time, key in would be trying to observe that in the somehow, or?
Well, we want to observe it on radar, but here's the thing. God, we're probably going to get 30 extra seconds lead time, right? Which is like, I want to go an hour. Everyone wants an hour. Okay, the storm hasn't formed yet. Oh, shit. How are we going to, I don't even know what the storm looks like yet. I can guess what it looks like based on the environment. But what you can do in the future, we'll probably do, run simulations like this based upon previous model forecasts, do a bunch of ensembles. I haven't talked about ensembles at all, but all my simulations, except for the super high resolution ones, are ensembles because they're so much more important to run on ensembles than a single simulation. Eventually, we're going to get ahead of storms by predicting them on the model. We'll get a much better forecast. It's going to happen. It's just going to be a pain in the butt. But that's what I do, so it keeps me out of trouble.
I guess that's kind of leading into my question is, do you think that the answer to this would be just getting down the model runtime, so where as you see these blowing up, you can be like, okay, mesoscale, fine, let's run a model.
Trigger that model, run it really fast, get ahead of the storm.
See if you get any
Yes,
like you see.
that is exactly what I hope. That's the future. And it's going to be GPUs. I keep on saying this, and you guys probably don't care.
I can only imagine the modeling.
The modeling is going to be, the model, it's going to be how do you get good inputs? Yeah, getting good inputs. Garbage in, garbage out. If you start with bad initial conditions, you're going to get a poor simulation. This is where data assimilation comes in. I stay away from data assimilation. It's all weird math, and it's like, it's important that we do it right. And there's a lot of really smart people working on this, but you have to assimilate radar, all this stuff into one thing that a model can understand, and then run the simulation, and then get ahead of the storm. We'll get there. Totally, we'll get there. But it might be 10 to 20 years. I just don't know.
And that's just waiting for horsepower to catch up?
Waiting for horsepower to catch up, waiting for the models to be tuned for that kind of thing, waiting for the data assimilation to be good enough. See, again, I say this like I know what I'm talking about. There's a lot of things that have to work right before we get to that point. We already have NCEP models running all the time, basically doing what I'm saying, only forecasting for the CONUS or whatnot. I want to do the same thing when it's go time. Severe weather day, we've been forecasting this big event for 5 days because the SPC is excellent at that. You got to admit, the one thing we do really well these days is where the outbreak's going to be in a few days, right? You guys have to acknowledge big props to SPC and what they do. You're seeing these regions like, okay, that prediction's been really good, but the prediction of tornadoes itself, we're not even close. We're not even close. So someday, but I don't know when.
But you're thinking at least 10, probably more than 20 years.
Yeah, I mean, to do an actual thing, what I said, when like we've got the storms just popped, get the environment, get it massaged so it's all, it's been assimilated, run the model. Run an ensemble. We'll just run the model. Run an ensemble. How many times we get a tornado, right? You don't just want to run the model once. You want to run it 50 times. Yeah. So
under different conditions.
It's all probabilistic. All forecasting is probabilistic, and people hate it because they want to know if it's going to rain tomorrow for their kid's baseball game. You tell them the 40% chance, and they say, they want to flip you off. But that's the way it works. I wish we were more, the general public was more in tune with well, I can't even say the word, so how can I expect anyone to understand it? Anyway, I guess I'm done.
Yes, we
All
have
right.
to steal you for a couple
No, that's
of interviews, but will you join us for dinner tonight, and then people can ask
Maybe. I'm not so sure yet.
questions?
Yeah,
Okay,
I'm not
let
so
us
sure
know.
yet. Yep.
We have just about a 10-minute break, and then we'll go into our next session.
Yeah.